Hello, it's Dr. Olson again for Physics 1053 College Physics 1 at Daytona State College. In the previous video, we looked at two-dimensional motion from Chapter 3 of our physics textbook. The purpose of this video is to take what we learned about two-dimensional motion and apply it to a specific example. This example is actually from the textbook, and we will get to that in just a second. But first, let me show you a few keys and tricks to solving physics problems in two-dimensional kinematics. First of all, if you really want to deal with the whole problem all at once, it can be very, very difficult. And frankly, the easiest way to do it is to use calculus. Now, we don't have that resource available to us, so we're going to make it a little bit easier. Instead of solving the whole problem in two dimensions, we're going to break this problem into two parts. We're going to take any vector we have, separate it into x and y components, and then solve the components separately. So instead of one two-dimensional problem, you now have two one-dimensional problems instead. Then we can just solve those separately, have them work together, and voila, you've got yourself an answer. So that's how we're going to approach solving two-dimensional kinematics problems. Recall from the previous video that all of your kinematic equations, they work perfectly well in either of the two dimensions that we're addressing. So you have the equations which we can apply for x, and we have the equations that we can apply for y as well. The exact same equation, just applied in a different direction. Now, when we deal with projectile motion, just recall that here in the y direction, our acceleration is generally due to gravity, so that would be a negative 9.8 meters per second squared. Also note that in the x direction, generally there is no acceleration in x. That's because there's nothing pushing it horizontally one way or another. That is, if you're ignoring air resistance. So acceleration would become zero, and that would simplify all those problems accordingly. So how we're going to do this is we're going to apply these equations to the x and the y components separately, and then use time to connect the information between x and y. Now, please, please, please be super careful. Do not start applying x component variables in y component equations, or vice versa. An x component variable will not translate into the y direction, and it will only mess up your answer. Okay, so let's revisit the process of solving a physics problem in two-dimensional kinematics. These steps can be used in future problems and adapted, and we definitely will do that. We will adapt them as we address new types of problems. But for two-dimensional kinematics, here's how we're going to solve them. First of all, we're going to read and reread the question, make sure we understand what is being asked. Second of all, we're going to make a picture to show and illustrate exactly what's happening. Third, we're going to make x and y coordinate systems. And then fourth, we'll separate all the x and y components using trigonometry. Fifth, we need to list everything we know and everything that we don't know. And I will add also here on the fifth step, we need to identify the variable that we are looking for, that the problem is wanting us to solve for. Step 6, now we choose an equation and solve algebraically for the variable that we need. Notice that in these first 6 steps, we have not once actually picked up a calculator. The calculations don't happen until step 7, when we finally start putting numbers into the equations after we've solved algebraically, and then we plug it into the calculator, get a solution, we check our results and our units. Okay, so here is an example from your textbook. This is example 3-5 on page 61. You have a movie stunt driver on a motorcycle speeding horizontally off a 50-meter high cliff. Question is, how fast must the motorcycle leave the cliff top to land on level ground below? Looking again really quickly at the problem, for some reason it's missing that he lands 90 meters away from the base of the cliff. That is important information. He will be landing 90 meters away from the base of the cliff. All right. So, first step, we read and we reread the question. Movie stunt driver on a motorcycle is speeding off horizontally. Note the word horizontal, that tells you what direction the velocity is. Initial height, he's on a 50-meter high cliff. How fast must the motorcycle leave the cliff to land on level ground below 90 meters away? Okay, so step 2, we draw our picture. We've got our 50-meter high cliff, landing 90 meters away. He doesn't travel in a straight line. Remember, he travels in a parabolic shape. So we cannot use Pythagorean theorem to solve this. We have to use kinematics. So there's our picture. It's also very helpful to indicate, well, what else do we know? We know that acceleration is downward. They don't but in this figure, but it would also be useful to say, oh, velocity is horizontal, so we can draw our initial velocity completely horizontal from where he's taking off. Step 3, let's choose our x and y coordinate systems. We need to choose our coordinate system such that the point where the sun, we need to choose a coordinate system so we have a reference point. So let's just choose the point where he leaves the cliff as our origin. So this is horizontal distance 0 and height 0 right here at the cliff. Now, anything that could be a vector, we separate into x and y components. That's step 4. Let's take velocity to start off with. So we have our initial velocity, which we still want to know, by the way. And he's traveling completely horizontally. Since he's going horizontally, what is the angle that he's taking off at? 0 degrees. So if we use trigonometry, we find that the x component would be v naught cosine of the angle, which is 0. But cosine of 0 is just 1, so that becomes v naught. Also, v naught y would be similar, only we use the sine function, but sine of 0 is 0, so there is no y component at all. Now, the easy way to think of this would actually be an easier way than using trigonometry is he's moving horizontally. The velocity is all in x direction, so the velocity is all in x direction. None of it goes in y. So v naught x would be v naught, and v naught y would be 0. Same story for the acceleration. We know that the acceleration is down, which means that there is no x component to it, so that's 0. And for the y component, it's down at a value of g, so it's negative 9.8 meters per second squared. Okay, step 5, list everything we know and don't know, and identify the desired variable. So here's a little table drawing in all the information that we know. We start x and y at 0 meters. Final distance in x is 90 meters from the base of the cliff. Final distance in y is at the bottom of the cliff, so 50 meters below where he starts. We don't know the initial velocity, but we do know it's 0 in the y direction. We don't know the final velocity at all, but we do know the accelerations. We're just missing time. Now, remember what the question said. It asks, how fast must he drive horizontally? So we're looking for speed, horizontal speed, so x, and we're looking right when he's leaving the cliff. That would be our initial point. So that is what we are looking for, is v naught x. So step 6, let's choose an equation to solve algebraically so that we can find the value for our desired variable. Of all of our equations, the one that would fit the best would be x equals x naught plus v naught xt plus 1/2 axt squared. And this is because we are looking for v naught x. We know the initial and final positions, and we know that the acceleration is 0. And since that's the case, then it becomes x equals v naught x times t. Solve for v naught x, it becomes x over t. However, we've got a problem here. Ideally, we would use an equation that we can just solve for the variable, plug in our numbers, calculate, and we're done. But we can't do that with any of our equations. We have to use the y component somehow. In this case, the closest we can get is this equation, but we're missing time. So how do we find time? Well, that's where the y component comes in. How can we find time? Well, out of all of the equations, you can look through, choose the one you want. But let's just use the same equation that we used before. This one actually works. The only other equation that involves time, there's a variable that we don't know, so that one wouldn't help. This is the only one that will help. So y equals y naught plus v naught y plus 1/2 ayt squared. Our initial position in y is 0. Our initial velocity in y is 0, so both of those cancel out. We're left with y equals 1/2 ayt squared. Solve for t, and it becomes the square root of 2y over ay. If you need a minute, feel free to pause the video here so you can come to that derivation yourself. Okay, so we've got two equations, one to solve for time, and then knowing time, we can solve for the initial velocity in x. So now, finally, step 7, we're ready to calculate our solution. For time, let's plug in our variables. We know that y is minus 50 meters from our chart, and acceleration is minus 9.8 meters per second squared, giving us a time of 3.1944 seconds. Now that we know the time, let's plug that into our other equation, where the initial velocity will be distance over time. So that'll be 90 meters, our x direction now, divided by our time of 3.1944 seconds, gives us a speed of about 28.2 meters per second after we round to the appropriate number of significant figures. So there's our answer, 28.2 meters per second. We're done, right? Not yet. There's still one more step. Check the results and the units. So we got an answer of a velocity of 28.2 meters per second. If he is truly in the air for 3.19 seconds, then using our velocity equals distance over time equation, solve for distance, sure enough, it goes 89.96 meters. Problem stated 90, but it's off because we rounded a little bit due to significant figures. So we're good. We've got a reasonable result. Now we just need to check the units. The units came out as meters per second. If we went through, we could do more of an analysis, just check all the units, make sure that they did come out properly. But since they did come out as meters per second, that is the proper unit for velocity. So our units checked out as well. Okay, that concludes this example. Go through this again, answer all your questions, make a list of questions, send your questions to me. I am happy to answer and to resolve any concerns you have.